All right, good morning, everyone. Shall we just start? Yeah. All right, so so this is part 2 of the algorithmic applications of high-dimensional geometry. Again, kind of as a repeat from yesterday, we're mostly talking about algorithmic efficiency of algorithms. And the main tools that are coming, slower, are coming from high-dimensional geometry. Okay, and again, kind of just to repeat kind of the perspective from yesterday is that kind of oftentimes kind of these tools in high-dimensional geometry are about taking kind of big objects and representing them somehow by smaller objects such that they approximate the properties that are useful for the problem at hand. Okay, and somehow that will help us in making algorithms more efficient. Okay, so yesterday we were talking about dimension reduction in Euclidean space, which basically says that there is a map that maps any high-dimensional space. You know, think about this kind of infinite-dimensional L2 into something much smaller, some k-dimensional space, such that the distance in the smaller in this smaller space well approximates the original distance up to 1 plus epsilon approximation with some probability, right? And these parameters can be achieved with target dimension, which is only a function of epsilon and delta. Okay, and then this has been useful for L2 regression, for example. Okay, so today we'll talk about, this will be, the second lecture will be about sketching, and this will be the third lecture. So now we'll talk about sketching, okay? And, before kind of defining what sketching is, let's ask the question, kind of the natural question is, okay, we can do L2 regression. But what about beyond L2? Okay, so for example, what if we want to solve L1 regression? Can we do the same for L1 regression? So L1 regression is exactly the same as L2 regression, except that we change the L2 norm. So argmin of the L2 norm, we want to change into argmin of L1 norm of the difference of AX minus B. Okay, exactly the same problem, but a different norm. Okay. So what do we do? Well, can we do dimension reduction for L1? Okay, so again, maybe I should define what L1 is. Right, so L1 of vector x is just summation of absolute values of the coordinates from 1 to d. Okay, just to make sure. Okay, so maybe we can do dimension reduction, the same style as Johnson-Strauss here, and do the same. Well, it turns out that for L1, the dimension reduction essentially doesn't exist. Okay, it's very, very far from what we can achieve for Euclidean space. So, for example, to make it concrete, if we have, let's say, n points, and we want target approximation d, think about this d as, this 1 plus epsilon, let's say even factor 2, then, there are theorems stating that the target dimension has to be something like n to omega 1 over d squared. So for dimension 2, this means some polynomial in n. Okay, and the best upper bound actually that we know is something like this, n divided by d. Okay, so the right dependence is not known at the moment, big open question, but it is known that it is, not only it has to depend on the number of points, but it has to depend polynomially. Okay, so to contrast this with the statements from yesterday, Johnson-Strauss showed that for L2, let's say for approximation 2, we can achieve dimension which is logarithmic in n. Okay, so this is qualitatively different kind of results. Okay, and there are even more bad news kind of than that, but let me just stop here. Okay, so what do we do then? Kind of, right? Is it is this entire theory kind of restricted to Euclidean space? Well, the answer is no. We can actually go beyond, but what we need to do is we need to generalize the notion of dimension reduction. Okay, and this is where sketching comes. And kind of to best describe where kind of introduce sketching, we'll basically think about dimension reduction from the computational perspective. Okay, so we'll really, you can think about, dimension reduction, the Johnson-Strauss lemma, it did come from functional analysis literature. Basically, mathematicians, came up with this notion, and, it has found uses in computer science. So think about kind of what we'll be doing next is, putting computer scientists kind of hats on us and thinking, well, let us kind of think computationally about this question of dimension reduction. In particular, what we've had so far is, we take, we have a map, this dimension reduction map, which mapped our metric, yesterday it was Euclidean space, today let's say it will be L1, into some lower dimensional space, let's say, real space of dimension k. Okay, so this was our map, have a bunch of points, we projected, we mapped them into some lower dimensional space, let's say 3-dimensional space, such that all distances are well approximated. Okay, so what we said is that, well, the original distance between 2 points x and y is well approximated by the L2 distance in this mapped space. Okay, this is how it was yesterday. Okay, and we say that, well, if the original space is L1 and this target space is L1, then we cannot really do this dimension reduction well. Okay, but you know, it is not super clear kind of that the target dimension necessarily has to be of the same type as the original space, and in particular that it has to be a metric at all. So how about we just say that, okay, we map into low dimensional space, k-dimensional space, but we don't necessarily compute L1 or L2 norm there, or any norm at all. Maybe it is just a computational procedure that takes this S of x, this low dimensional representation of x, low dimensional representation of y, does some kind of computation, and spits out a number, which is a good approximation to this distance. Okay, so this is what it will be. Now, you know, what are the disadvantages of considering this more general definition? Well, one is that, I mean, once it's a computational, kind of some computational procedure that takes, you know, two, you know, k-dimensional vectors, you know, does some, you know, computation, it might not give a metric, right? So this C of, you know, defined on RK might not satisfy triangle inequalities and, you know, other metric properties, for example. Okay, so there is less geometric structure, which, you know, might hurt us in developing algorithm. On the other hand, you know, once we generalize the notion, of course, we have a proof that, well, it is more expressive. Perhaps we can do, you know, better trade-offs than if C were to be forced to be a metric. Okay, so this S is what we'll call sketch, right? So in general, it maps metric into some lower dimensional space or some sketch, basically, of dimension k, of size k, and such that there is an estimation procedure C, such that, you know, given these two sketches, it spits out a number that well approximates the original distance. Okay, so think about this as the generalization of dimension reduction. This is this functional compression scheme that basically, you know, again, takes these points in this M, which we think about high-dimensional space, produces these compressions, sketches, really, and you know, think about these sketches as being designed specifically for the purpose of computing distances between different points. Okay, and again, you know, it will be lossy, randomized, you know, as the caveat that we started with yesterday. Okay. Okay, so this is kind of, you know, high-level perspective. So we'll try to design a sketch. So, okay, and I should mention that, you know, kind of as, you know, oftentimes we'll think about sketches as, you know, not really mapping into real space, but let's say in binary space, this is slightly more kind of really computational view where, you know, you can't really store real numbers. You really talk about, you know, how many bits can you store. Mostly I'll still stick to RK just because, you know, it is easier to talk about, but, you know, at the end of the day, you can also map into binary strings with kind of some caveats, but this distinction won't be really important, but, you know, just saying that kind of computationally, strictly computationally, we should be talking about binary strings of size k. Okay, so let's design this kind of sketching for L1. Can we do this for L1? Okay, so, you know, obviously, if I'm asking this question, setting this up, you know, the answer will be yes. But how shall we do? How shall we design such sketches for L1? Okay, so first of all, let's try to kind of, in a sense, go back and try somehow to design still a dimension reduction for L1. And say, well, how, you know, there is some kind of procedure for designing this dimension reduction for Euclidean space. So let's try to simulate this procedure to L1 with appropriate, you know, changes. Okay. In particular, is there an equivalent of these Euclidean projections? Okay. So in Euclidean space, what we've done, we, you know, pick a random subspace or this random Gaussian matrix and project using this random Gaussian matrix. Okay, so for L2, this was, you know, why did we choose these Gaussian matrices to do this projection into a low-dimensional space? Well, because of the stability property. Did Jarek mention the word stability property yesterday? Kind of, but, well, basically, you know, stability property means this property of the Gaussian variables. This is what appears on Wikipedia if you look up about Gaussian distribution, that for any real numbers z1, z2 up to zd, and if g1, g2 up to gd are Gaussian random variables, which are IID, then the summation of them is exactly distributed as another Gaussian variable g times VL2 norm of z. Okay, this is what we used for the Gaussian distribution. This is what you can, having this property is enough to prove Johnson-Strauss lemma, for example. Okay, this is the main property that one uses of the Gaussian distribution. Okay, yes, just to make sure that it connects to yesterday. Okay, and okay, so this is the property, and it is not normal to ask, like, well, there is the Gaussian distribution. Basically, you choose Gaussian distribution to do dimension reduction in L2 because it has this property that you sum them up in this linear form, and you get something, another distribution times VL2 norm of z. Well, is there some other distribution to replace this g's with, so that at the end of the day we get the same thing, except that this is not L2 norm but L1 norm? Okay, it turns out that yes, there is a distribution. It's called Cauchy distribution. Here is its PDF. It won't really, matter for us. This is how it looks like pictorially, but it is roughly, PDF of S is 1 over S squared plus 1 up to normalization. Okay, good. So what does it mean? Well, it is what is called one stable. Okay, the equivalent notion of this, but instead of L2 norm, L1 norm. But if you choose C1, C2 up to CD from this Cauchy distribution, IID, you take this linear form, then this quantity is distributed as yet another Cauchy distribution times the L1 norm of Z. Okay, so this is exactly equivalent of this, except that the distribution is different, but instead of L2 we get L1, and voila. So okay, why don't we use this for dimension reduction, and why don't we get dimension reduction for L1? Right? We have just replace Gaussian distributions of Cauchy. Sounds like we should be done. Well, the issue is that the Cauchy distributions, unlike Gaussian distributions, are heavy-tailed. Okay, so for Gaussian distribution, the PDF is roughly decays exponentially fast. This decays only polynomially fast. And this is an issue. For example, just to kind of, I guess, give you an example. Well, for Cauchy distribution, of course, the expectation is 0 just because it's symmetric distribution. But if you, let's say, take absolute value of the Cauchy distribution and take its expectation, it already doesn't have, it's not finite anymore. Okay, this is very unlike for Gaussian distributions. Even furthermore, this means that higher moments of the Cauchy distribution will be, even less divergent. Okay, and this is pretty much how we used to prove Johnson-Strauss, kind of, by looking at the moments of the Gaussian distributions, and proves that they, are bounded, and that was good for us. Here we don't have that. Even the first moment is not finite anymore. So we won't be able to prove any kind of concentration of this quantity. Okay, this is why the dimension reduction, similar to Johnson-Strauss, does not exist for L1. This is not the reason, but this is why this does not give it. Okay, but can we still do something? And this is kind of the idea introduced by Piotr in 2000s. Basically, what you can do, you can use this to do sketching for L1. Okay, so if you, again, put more of computational science kind of hat on you, then suddenly you can do a form of dimension reduction. Okay, in particular, we can define a similar map. Okay, exactly like before. Instead of, namely, you take your input x that you want to sketch, you multiply by a matrix where each entry is chosen ID from the Cauchy distribution now, instead of Gaussian. Okay, which will denote the different rows will be C1, C2 up to Ck. Okay, and again, kind of to try to analyze, in a sense, the difference between these two sketches, we want to look, given 2 points x and y, we want to look at the difference of the two sketches and somehow use that difference, which is a k-dimensional vector, to estimate the L1 norm of the distance between x and y. Okay, so by linearity, we can write that s of x minus s of y is just, this matrix cx minus cy, bilinearity. This means that it's just the sketch of the x minus y, and we'll just denote this difference between x minus y by z. Okay, and we'll analyze this quantity, cz, which is again is a k-dimensional vector, and somehow from this quantity, cz, we want to estimate the L1 norm of z. Okay. Note that each coordinate of this is distributed as L1 norm of z times a Cauchy distribution, just by one stability of Cauchy distribution. Okay, so if we were to do exactly the JL analog of of this map, then we would take L1 norm of a projection, namely CZ. But again, I said this doesn't have any finite expectation or moments. But what we can do instead, basically instead of computing L1 norm of this, we'll take the median of this quantity. Or more formally, we'll take, it's a k-dimensional vector. We take absolute value of each coordinate, and then we take median of that. Okay, so this is where kind of really the difference between kind of mathematical formula versus kind of more computational view comes in. Median is a very kind of computational thing, and definitely this kind of thing won't give you a metric. Okay, so and this is really the estimate. Okay. So again, to estimate the distance between L1 distance between x and y, you take their sketches, take the difference, right? You obtain a k-dimensional vector. You take absolute value of each coordinate and take median of that. This is the estimate. We'll prove that this is equal to this well approximates the L1 norm of z or L1 distance between x and y. Okay. So to prove that, the main correctness claim will be the following: that for each coordinate I, ranging from 1 to k, this value, right, each of these kind of components, so CIZ in absolute value is at least the L1 norm of z up to this 1 minus epsilon with probability a little bit more than half, and it is upper bounded by this L1 norm up to 1 plus epsilon, again with probability a little bit more than half. Okay, this is the main correctness claim, and in a sense where we'll use the properties of Cauchy distributions. Okay, so let's prove that. Okay, so this is the claim that we want to prove. So here's the proof. It's pretty simple. Well, again, we fix I, we take this quantity, Ci times z. Again, this is a vector of Cauchy random variables. This is just a fixed vector z. Okay, just by the one stability of the Cauchy distribution, this quantity inside the absolute value is exactly distributed as the L1 norm of z times another Cauchy variable c. Okay, so this is just a constant. You can pull it out. Right? So what remains is that L1 norm of z times the absolute value of a Cauchy random variable. Okay, so now we compare. So this quantity is equal to this one. We compare it to L1 norm of z times 1 minus epsilon, let's say. Okay. So the L1 norm of z cancels out. The only thing, given this fact, the only thing that remains from these claims to prove is that the probability that over a random choice of a Cauchy random variable, but its absolute value is bigger than 1 minus epsilon with some probability a little bit more than half, and it is upper bounded by 1 plus epsilon with probability a little bit more than half. Okay, now this is purely, a mathematical calculation at this moment. There is no vector z anymore. It is purely a claim about Cauchy random variables here. Okay, so, and then you kind of can go and verify that this holds for the Cauchy random variable. Okay, in particular, its median is, median of the absolute value of the Cauchy random variable is 1. So you expect that, if we put this barrier a little bit less than 1, then, the probability will be a little bit more than half, and same here. Okay, and that this is the right dependence on epsilon. This is just a matter of verification that I won't do in this lecture. Okay, so basically, model of this verification, we have proven this correctness claim. And now let's use this claim to prove that our estimator, right, for the L1 norm of z, in particular with median of these quantities, is a good approximation up to 1 plus minus epsilon of the L1 norm of z. Okay. In particular, we'll take k, which is equal to order of 1 over epsilon squared log 1 over delta, again, to achieve a delta error and 1 plus minus epsilon approximation. Note that this is up to constants, exactly the same formula that we got from dimension reduction in Johnson-Strauss lemma. Okay, it's exactly the same up to this order of. Okay, and the reason it is because of how CLT central limit theorems look like. Okay, so indeed we'll use another central limit theorem to prove this claim, to prove that the estimator is good. So here is how we do it. Okay, so for each coordinate I, we introduce another random variable called Li. Okay, it's indicator random variable which is equal to 1 if this is satisfied. Okay, this happens. So in particular, this means that the expectation of Li, where Li will be equal to 1 with probability a little bit more than half, so half plus omega epsilon. So this means that the expectation of the summation of Li's, where I ranges from 1 to k, is at least k times the expectation of each of them, which is half plus omega epsilon, right? Exactly this quantity here. Now, what do we have? We have a summation of IAD random variables, right? Each of these CI is an independent random Cauchy vector, hence these, all these events are independent from each other. So we have a summation of k indicator random variables, which are IAD. Their expectation is at least k times half plus omega epsilon. Okay, so this means that the probability that the summation drops is smaller than k by 2 is, the expectation is a little bit more than k by 2 by this epsilon k. What is the probability is smaller than k by 2? Well, for this choice of k, it is less than delta, and this follows from just a standard Chernev bound or central limit theorem. Okay, so this means that at least 50%, right? What does this, what is the converse of this? Right, that the summation of Li's is more than half. This means that for more than half of these coordinates, they're at least as large as L1 norm of z times 1 minus epsilon. Okay, very similarly, we can prove the other direction. So define ui to be equal 1 if this holds. Very similarly, we can prove that for at least 50% of coordinates I, this will hold. Namely, this absolute value of CIZ is less than L1 norm of z up to 1 plus epsilon factor. So again, 50% of these ones are at least L1 norm of z 1 minus epsilon. 50% of these ones are at most L1 norm of z times 1 plus epsilon. This means that if you take the median, it will satisfy both of these. Okay, so this means that assuming that this holds for this holds for Li's and the same holds for UI's. Okay, the median of all these quantities will be between 1 minus epsilon and 1 plus epsilon times L1 norm of z. And this happens with probability at most 2 delta. Voila. Yes. Right. So what is the summation of Li's? By linearity of expectation, we have that this is summation of the expectation of Li's. Each Li, what is the expectation of a fixed Li, let's say L1? Well, expectation of L1 is, since indicator random variable, it's exactly the probability that L1 is equal to 1. Well, what does it mean? It means that this is satisfied. And this is what we proved on the previous slide, that this happens with probability at least half plus omega epsilon. So this means that indicator of each, expectation of each Li is at least half plus omega epsilon. There are k of them, and so this means it's the expectation of the summation of Li's is at least k times the expectation of each of them, which is half plus omega epsilon. Okay. Any other questions? Okay, and voila, we get this, right? This is right? And it was, the way the probabilities work out here, it was important to take the median as opposed to some other estimator. Okay. All right. So this is how you get a sketch for L1, and it turns out that you can use it for L1 regression as well. To get an algorithm for L1 regression, and I mean, note that kind of it's hard to use it directly, kind of, because what we did for L2 regression is that we take a big problem, we apply dimension reduction to it, and we reduce to a smaller problem, which was still L2 regression. Here, note that if we do this dimension reduction, kind of the norm to which we reduce is kind of median. So, there isn't an easy algorithm to do even a smaller dimensional median regression. You can still use it in a slightly different way than how the sketch suggests. In particular, you can define, what I'll call here as a very weak dimension reduction. Okay, so now it looks more like an actual dimension reduction. Namely, we take a map S, a linear map S, and we compare the L1 norm of projection, or this sketch, or the dimension reduced point, namely S of P, to its L1 norm of P. And the weak dimension reduction has the guarantee that this ratio, basically, the approximation is between 1 and 1 over delta with probability which is roughly 1 minus order delta. Okay? Note that the approximation here that we get depends on this delta. This is pretty bad. This is very, very different from what we had from normal dimension reduction. But this is somehow enough for us. In particular, this map S can be taken, let's say, as again, multiplying by a Cauchy matrix, or also you can replace Cauchy variables with 1 over exponential. There are different ways to do it, of different advantages. But from this weak dimension reduction, we can also obtain weak oblivious subspace embedding, right? This kind of stronger dimension reduction that holds for any subspace. And in particular, what property it will have, that we can use this weak dimension reduction to obtain this weak oblivious subspace embedding, is that we get a map, again, that maps, let's say, n-dimensional space into k-dimensional space, such that for any linear subspace of dimension d, okay, so this is so far exactly like it was for oblivious subspace embedding yesterday. For any point P in this subspace, the L1 norm of a projected point is equal to the original L1 norm up to a factor of d to some constant. Okay, so yesterday this was not a d to some constant, this was 1 plus epsilon. Okay, so this for 1 we get a much weaker oblivious subspace embedding where the approximation is much, much higher. It depends on the dimension of this linear subspace. Okay, so it gives some polynomial. So now this, I mean, and the target dimension k that one needs to take is roughly d times log d. So that sounds bad. It's like, are we getting L1 regression up to this polynomial in the approximation? Well, kind of, in the first iteration, yes, but then you can apply, more techniques, in particular this preconditioner idea, to reduce the approximation to 1 plus epsilon. Okay, think about this, as this will give you some L1 regression that gives you a very coarse approximation, but only polynomial in dimension, as opposed to, let's say, in n. You can iterate this process to get a better approximation later on. Okay, basically using our techniques. And again, kind of to do this, I mean, here we again are faced with a problem that just multiplying with sketching all our data set points, this matrix A, would take too much time. So you need to create this matrix S, this sketching matrix or this linear map, to be kind of efficient. Particular computing sketches of all the points should be much more efficient than just multiplying by matrices. So indeed, you can design a map S, which is more structured in a similar fashion like we discussed yesterday at the end of the lecture, to get a better algorithm. And at the end of the day, the type of runtime that you get is, again, number of non-zeros of the matrix A, of the input matrix A, of the data set times log n, and something which is polynomial in d by epsilon. And as far as I know, maybe it is not known how to improve this dependence on epsilon from polynomial in 1 over epsilon to logarithmic in 1 over epsilon. Okay, and I should mention that these kind of applications of kind of dimension reduction and sketching have been very useful for many other kind of related numerical linear algebra problems, in particular regression under other norms like LPs or fancier things like estimator or Orlish norms, but also for other related numerical linear algebra problems such as low rank approximation of a matrix, matrix multiplication, and others. Again, there is a very good survey by David Woodruff from 2014. It's a little bit dated now, since more progress happens, but it's a good introduction to this if you're interested. Okay, any questions? All right, so if not, I'll move basically to the application I wanted to discuss more today, namely streaming. And this is a router, like a picture of a router. And here we'll change a little bit what we want, actually, what we're after. Okay, so far we're saying that, okay, let's use these techniques to get faster algorithms, right, to make regression faster. Okay, here what we'll ask is, well, let's make algorithms efficiently in a different way. In particular, let's make algorithms use less space. Okay, so space will be our kind of goal number one to optimize. Okay, and here is the motivation for that. Let's say we have a router which sits somewhere at the boundary of some network. Okay, it has a bunch of traffic kind of passing through, right? And it's lots of traffic. Could be gigabytes, terabytes, and what this kind of router wants to do is perhaps have some kind of a view of the traffic that happened, right, or a sketch of the traffic that has happened. So you can think about, one way to kind of represent the traffic is, to have a table where, let's say, for each IP, a packet with some, destination IP, for example, we have the frequency of how many times it happened. Okay, I mean, these tables are, of course, like much, much, much larger because, the traffic per day, let's say, that the router sees is much larger than that. But, I mean, what the router wants is some kind of sketch of this table, okay? So that, perhaps later it can give some kind of statistics about the data that has passed. Okay, so think about this as, for network analysts who, at the end of the day, says like, well, there was some, I don't know, denial of service attack. Maybe I want to kind of see what is the IP that was kind of most frequent, or, some kind of statistic of this table, basically, of the frequency table of the traffic that it has seen. Okay, and it wants to do this. Of course, the natural way is to just store the entire table, but this table is humongous. This is orders of magnitude larger than the memory of a router, which is, let's say, maybe in megabytes. Okay, so it really wants to somehow kind of a sketch, a compression of this table, store on the router. Okay, and you can see that I deliberately kind of use the word sketch here because, it pretty much corresponds to what, how we define sketch, namely, it is some kind of representation of big data into much kind of smaller representation, but while preserving some kind of information that we care about. Okay, so these sketches in general will depend on the type of problems we want to solve later on. Okay, so let's make this a little bit more formal. So suppose, really kind of the traffic for us is, some kind of packets that have IPs. And basically what we can do from this, the information we want to extract, let's say, is, frequency type information. Okay, so for each IP called I, we have xi, which is the frequency of that IP, how many packets of that IP pass through. Okay, so xi is now a very high dimensional vector. Right, or x is a very high-dimensional vector because the number of IPs, let's say, is 2 to 32. Okay, and we want some kind of statistics to be able to, at the end of the day, to say some kind of statistics about this vector x. Okay, so what are the kind of statistics? Well, let's say the first moment. Right, this is really how many packets they pass through. Well, just summation of xi's. Well, this is easy, right? We don't need to store the entire vector x. We can just store a counter, but each time we see a next item, basically a next packet, we just increment a counter. This this counter will just store the summation of xi. So it's very easy to update when we see, as the traffic passes by the router. Okay, here's a little bit harder thing. Second moment. Let's say we want to see the variance of this frequency vector. Okay, so somehow, perhaps the variance is larger when this is slightly abnormal. Perhaps. Right, so again, variance, what does it mean? Well, it's basically L2 norm squared of a vector, so summation of xi squared. Can we somehow store a small sketch that at the end of the day, the network analyst comes and asks the router, well, tell me what is the L2 norm of the frequency vector of the traffic you have seen? What do you guys think? Sorry? So, imagine this vector x is very, very high, much larger than, suppose we just store one counter, right? Then, if the only thing we store is summation of xi squared, suppose, IP 100 increments in frequency. We don't know what is the current value. It depends, the increment to this counter depends on what is the current frequency of this IP 100, let's say. Right, so if we, just to make it simple, right, if x is equal to, let's say, 1, 1, let's say this is 2, right, 0, 0, and so forth, right, versus x equals to 2, 1, 0, 0, right? Okay, so both of these things have L2 norm, which is the same, which is 5, right? The second moment is 5. So, but now suppose we see another copy of IP2, right? So this gets incremented, right? So if it was this vector, then the new vector becomes 1, 3, and 0, 0, 0, 0, right? And if this was the vector so far, and we increment again, the IP2 appears again, right? This becomes 2, 2, 0, 0, right? I mean, the second moment of this one is 10, second moment of this one is 8. So just by knowing the current, second moment, we don't know to distinguish whether it's this vector and this vector. So we don't know if we're seeing a second copy of the IP2, the new second moment is 10 or 8. Okay, basically what I'm saying is that, when we increment some counter, to know by how, when we increment some xi by 1, to know how much the second moment increases, we need to know what is the current value of that xi. Yes?
What if you use some kind of hash table?
Okay.
And then just use the value of the hash table to calculate the right amount?
Right, so you're saying kind of, just to distinguish these two things, just hash into different things. This idea is used for something else, and it is useful in general, but with caveats. But there is I guess, slightly, simpler answer, I guess, right? We'll get to something like hash tables in a bit, but before that, let's think about this kind of directly. So the answer is yes and no. So let me start with the answer no. But no, we cannot store a small sketch that will estimate this exactly. Okay, so there is a lower bound. We need to do approximation to be able to reduce the space from kind of the trivially storing the entire table. Okay, so we'll do this approximately. How can we do this approximately? How can we do this approximately? This is a test whether you've been attentive for the last day and half hour.
So you commented that one of them by one won't move the current to the norm much, like
Say again?
incrementing one of those things by one won't move the current to norm by much. So
Well, I'm saying that it depends. It depends on which vector it is, right? We are
but at the end you are going to increment just one of those entries, right, by one also.
right.
So like let's say if it was 0, 0, 0 and the current norm is n,
Mm-hmm.
norm, so the next and if you increment that one, the next would be n plus 1.
Well, if you incremented something which was 0 by 1, then the second moment increments only by 1. If you increment something which had value 100 now, incremented by 1, then the second moment increases by,
Times square root of 2 times 100 plus.
yes, something like that, yeah.
So you can get approximation like so that something is less than current norm. That 100 that you said is less than current norm.
Well, I mean, so the dimension, so let's say the dimension is n, right, which we think of something like 2 to 32. Okay? And suppose the current L2 squared norm is equal to 2 to 32. Okay? So we don't know whether x is equal to 1, 1. We've seen one copy of each IP, or x is equal to 2 to 16 and 0, 0, 0. Okay? And now you see a 1 coming in. Right, so in general, this is what's called this root n. Right? You see one, the first coordinate, another copy of the first element. Well, if it is this case, then increment is something like 2. Right? If it is this one, the increment is pretty large. Is root n.
Right, but it's correlated with the current number, current value of the number.
Yes, it is correlated, but there is error that is being accumulated over time. As in,
Yes, you're
okay. Okay, so the answer I was hoping that you guys would say that, well, perhaps this is a high-dimensional vector. We are really estimating its L2 norm. Well, maybe you can use dimension reduction for that somehow, right? To store it with much smaller space. Okay, so again, for L2 moment, we'll just store a sketch which is exactly the dimension reduced vector x. Right? So what does it mean? Well, for the current vector x, we just store, just pick the Gaussian matrix randomly, again, of some dimension, k by n, where k will be, something like 1 over epsilon squared. Okay, and we store this. So we store the dimension reduced vector x. Okay. We need to know this matrix, and this matrix can be large, and it is an issue kind of to be careful. But think about we choose this matrix kind of pseudo-randomly, so we have an efficient way to store it somehow. Okay, I mean this is something that will be dealt with, and it can be dealt with. I just don't want to go into the detail of that. Okay, so what will be our estimator? Well, the estimator is that, well, we know kind of by Johnson-Strauss lemma that if we take L2 norm of this, let's say squared, then this will be a good approximation. This is the matrix. Doesn't say here. But the L2 squared norm of this sketch will be a good approximation up to 1 plus minus epsilon factor of the L2 norm of x. So this estimator will give a very good estimate of the L2 norm squared of vector x. Okay? Does that make sense? So, I mean, now what I'm describing is, what should happen at a fixed time, I'm not, it's kind of static kind of description, as opposed to what should be describing is dynamic description. How do we update this sketch as we see another API, for example? Well, this is where we'll use the linearity, okay? So let's say we encounter an API, okay? So g of x is the previous sketch so far, right? It's like the sketch from which we're updating, right? So this is the previous one. What should be the new sketch, right? So this is the new updated vector, right? So this is x, what we had so far. We've seen IPI. This means that coordinate I is increased, right? So this means that the new frequency vector is x plus EI, where this is the basis vector. Okay, this should be the new sketch. Well, by linearity, we can write that this is equal to gx plus GEI. Right? This turns out to be exactly the previous sketch. And this is just a column of G, the ith column of G. So this means that when we see an API, the only thing that we need to do to update this sketch is to basically take the previous sketch that we have, add the ith column of G, and this is the new sketch. Okay, so this is kind of similar, kind of in spirit to kind of homomorphic encryption, right? Where you don't need to this is in kind of the notion in cryptography where you have data which is encrypted and you do processing in your data in encrypted form without ever decrypting it. Okay, so the same here in a sense. To update the sketch of a new vector, we don't need to find out what is the vector, update the vector, and then apply the sketching again. Just by linearity, we can update the sketch of our frequency vector directly. Okay, kind of this is the beauty of linearity. Okay, makes sense? Daniel, until what time shall I go for the first lecture? 10:15, I think, even if I started a bit late. Okay. So let me tell you kind of a slightly different problem, just to give you a different algorithm, right? That's for the application. So far we just use dimension reduction. So let's consider a different problem, and this might feel even more natural than, let's say, estimating the second moment of a frequency vector. In particular, counting how many different vectors have we seen, how many different IPs have we seen. Okay, so number of distinct elements, in particular, given the frequency vector x, how many non-zeros are there? Okay, this is also called number of distinct elements because we just count the number of distinct IPs that you've seen. And kind of, to connect it to kind of moments, you can think about this as kind of the zeroth moment, really. Right, so it's kind of the L0 norm of a vector x. Okay, and it's true kind of in the limit. Okay, so can we do something here? And again, I want to do this kind of with small space. Again, trivial solution is, let's say to, I guess, slight improvement over, just storing the entire vector of IPs is that, if you have distinct elements, but you need just space pretty much order D. Okay, and you cannot really do better if you want to estimate the number of distinct elements exactly. Okay, but once we allow approximation and some randomization, we'll see that we can do this. We improve the space complexity from D to log D. So log number of distinct elements. Okay, so and in fact this can be improved and then forward to log D, but this is beyond what I wanted to say today. So let's see how to do this. This is kind of a very nice algorithm. This is kind of one of the perhaps the first algorithm actually in streaming in this model by Flageolet Martin from '85. And this is how it works. It's yeah, very good. Okay, I'll tell you the algorithm, right? And then we'll see why it works. So the algorithm is as follows. We pick. So U is the universe of the items, right? This is the in our case, if n is the dimension, then u is really u is equal to 1 to up to n. Okay, so this is the universe of possible items that we see in the stream. Okay, or basically the index of the dimension. Okay, so pick a hash function that maps this universe into real interval from 0 to 1. Again, we pick random reals. We can't really do this in practice, but stick with me for a moment. That won't be a very big issue. But let's assume that we can pick these real randoms. There are random reals. Okay, so this is a hash function again. Somehow we have access to this hash function. We can store it. Okay, so let's not worry about that issue. What we will store is basically the min hash. So what is min hash is minimum over all the items that we have seen so far of the hash of the item, right? So it is minimum over all items I that we have seen so far, or all coordinates which have been updated, of the hash value of the corresponding coordinate I. Okay, so here is the full algorithm, but before kind of explaining what is the output, let me show kind of pictorially. So here is how the algorithm works, kind of on a simple example. So here is the real interval between 0 and 1. Okay, and we'll store the min hash of the items that we have seen so far. So suppose first we see an item 2 in the stream. Right, so this means that coordinate 2 has been updated, right? IP2, we have seen it. Right, it maps to some real number, h of 2. Okay, so we'll store this as a minimum so far. Then we see another item, 5, here, for example, right? So we update the min hash to be this one, h of 5. Okay, when we see item 7, it maps here somewhere. We say, well, this is bigger than our current minimum, so we don't update it. Okay, and then we see more items. If some item repeats, then it obviously doesn't change the minimum min hash, right? So it should be obvious that repeats of items don't do anything for us really. Okay, so it goes on. Okay, and bunch of items, and let's say this is the min hash. Okay, we have seen what 1, 2, 3, 8, 7 different items. Okay, and what our output will be is basically 1 over this min hash minus 1. Okay, and right, so this min hash is basically this value, right? The distance between 0 and the first arrow. And the main claim is that the expected value of this is equal to 1 over d plus 1. Can somebody tell me an intuitive? I'll prove this formally. I mean, it's actually 3 lines to prove it formally. But is there? Can somebody think about this intuitively? Why this quantity should be 1 over d plus 1? Well, how many different arrows are there? Okay, where these number of distinct elements. Well, there are d arrows. All these different items, they're completely random here, IID. Okay, so kind of idealistically, then perhaps they're equally spaced. This means the number of intervals from 0 to the first arrow, from the first arrow to the second arrow, and so forth. The number of intervals is d plus 1. So we expect that each of these intervals should be roughly 1 over d plus 1. Or more formally, that the expectation of this quantity is 1 over d plus 1. Okay, and here is the proof. Again, as mentioned, repeats of the same element don't matter, right? Because it won't affect this formula. Okay, so let z be the minimum of d random numbers in 0, 1. Right, so we want to prove that the expectation of z is 1 over d plus 1. Okay, so to prove this, we'll analyze this expectation of z in two different ways. Okay, and here how it goes. It's very cute proof. So you pick another random number a from 0 to 1. Okay, and what we'll compute is what is the probability that a is less than z. And we'll compute this in two different ways. So way number one is that, well, one way to compute what is the probability that a is less than z, well, it is exactly equal to z. Right, so z is this quantity. You pick a random number a, what is the probability that it is this interval? Well, it is equal to exactly the size of the interval divided by the entire thing. And so it's z by 1, so it's z. Okay, what is a different way to compute this probability, a less than z? Okay, so what is z? Z is minimum between d numbers. A is yet another random number. What is the probability is that a is less than z? Sorry? Well, I mean, this is one way to compute. I want a different way to compute z, just to connect it to something else, yeah. Again, we can interpret this event differently, right? So we have z is chosen as minimum of d numbers, right? So we pick d numbers. We pick yet another number a. Again, all of them are ID randomly from interval 0 to 1. We say, what is the probability that this last number we have chosen is the smallest of them all? They are chosen as real numbers in the interval from 0 to 1. Yeah, so we picked 9 random numbers, right? So d is equal to 8, let's say. You pick 9 random numbers in the interval from 0 to 1. What is the probability that the 9th number that we've chosen is the smallest of them all? Yeah, exactly. It's 1 over 9. So the probability that a, the last number we've chosen, is the smallest among all of them is exactly, the probability that, the last item out of, d plus 1 random ID reals is the smallest, right? It's 1 over d plus 1. Okay, this proves that the expectation of z is equal to 1 over d plus 1. Okay, so, I mean, again, this is just expectation, and one has to prove some kind of concentration to say that, this output is good, and indeed, I mean, this doesn't concentrate well, but you can repeat this a bunch of time and take the majority answer. Okay, so instead of just storing just one min hash, you store k of them, right? And each of them kind of an independent algorithm, a dependent trial. Okay, each of them will give an estimate right from here. You take the median, not majority, sorry. Take the median of them, and for k, which is equal to this, again, coming from CLT repetitions, and you can prove again that you get a 1 plus minus epsilon approximation of probability at least 1 minus delta. Okay, and since we're kind of out of time, I'll stop here. Yeah. And we'll continue, I guess, in about 10 minutes with the third part, right? Oh, at 11. Okay. Okay. Well. Sorry. So the first is 1 hour, right?